Hello everyone, my name is Pranav Ravella, and I am currently a junior at Thomas Jefferson High School for Science and Technology in Alexandria, Virginia. Along with Raffu Khondaker, Eugene Choi, and Irfan Nafi, we designed Atheia, ensuring the safety and independence of people with visual impairments through intelligent observations performed through Redis. We hope that through our systems, we can inspire other high schoolers to utilize their resources to creative assistive technology devices that can empower the communities like ours. This is a quick agenda of the slides that we will be going over today. Our team, we're a group of juniors in the Thomas Jefferson High School area, and we seek to make a difference through our device and our actual solution. We met through a hackathon and a couple of science fair projects, and we hope to advance this project throughout and eventually deploy it to market later on in the future. Our problem. Meet Julie, a doctor turned trapeze artist and dancer. At 42, she cannot see the faces of her own children. She was going blind. Suddenly, she had to make the scary transition from a seeing world to a sightless one. Things she took for granted, searching for baby bottles, reading prescription labels, and even looking for misplaced items became difficult. But her biggest concern was her spatial awareness outdoors. She said she was an easy target to crime, and she's not alone. Crimes against the visually impaired are 3 times more likely. That's why we created Atheia, built by co-designers for co-designers. Co-designer stories like Julie's gravitated us to find a solution into the presiding problems with the current technology within the visually impaired field. Listening to our co-designers' stories and seeing their excitement about such a device motivated us to continue reiterating over the design to make it apt for the general user base. Furthermore, after understanding that 64% of people with visual impairments are unemployed, while current market devices are around $4,000 to $5,000, we understood that users wanted a non-intrusive, affordable device that was fashionable and discreet, but accessible to their needs. Atheia provides this functionality, and it's an all-in-one mobile app accompanied by a haptic bracelet that helps users navigate and understand any 3D environment. The phone can be quickly detached from the user's hip for active use and operated through audio commands. Here's a quick demo of one example feature that we have called Search. Raffu will be detailing more about this feature in the next section.
Atheia focuses on keeping the user safe, being accessible for everyone, navigating the user in 3D space, and of course daily use. This is a quick summary of all of our features. We'll go into each one of these in the following slides. Our first feature is image description, as shown in this demo.
Atheia, description.
Person playing with basketball outside a house.
For captioning, we use Azure Cognitive Services. This gives you a quick and concise description of your environment, allowing you to have a general situational understanding. Unlike image description, scan identifies specific objects in the user's view field and the frequency that they occur at.
Atheia, scan.
2 cars, 1 person, 1 ball, 1 building.
Note that all of our commands are given through voice commands, allowing for hands-free use. So unlike image description, scan identifies specific objects in the user's view field and the frequency that they occur at. So we have 2 modes, online and offline mode. Online mode has high accuracy predictions using an ensemble utilizing multiple computer vision models. Each of our models are run on the cloud through an Azure virtual machine. The one model that is run locally, YOLO v5, works with the other models, Detectron v2 and YOLO v4, with the latter 2 on the virtual machine. The ensemble consolidates all predictions for a final high accuracy prediction. Offline mode provides a shorter time lag and can operate anywhere. So instead of an ensemble, we use the second best option for this mode, YOLO v5, which is the leading object detection model compiled on iOS. With one model, we make more conservative predictions to avoid false positives. So while we typically have less detected objects in offline mode, the accuracy for the objects that are detected are very high. In the previous demo, we ran an online scan. Offline scan, as shown in this picture, cannot detect the house in the background. It only runs YOLV5. Our next feature, search, guides a user to specific objects while avoiding obstacles in 3D space.
Search for bottle.
Searching for bottle.
As you can see in the bottom left, this is the path they're following, and the haptic bracelet, which is on his wrist, guides the user towards the object. In actuality, the LEDs are replaced with vibration motors, as the user can feel the vibrations. For demonstration purposes, we use LEDs instead. To develop this algorithm, we had to take a look at a lot of existing papers. Since object guided, this area is very popular for autonomous vehicles, as they have to get depth measurements and classify objects around them. We use a novel method that uses Gaussian potential fields for object avoidance. Essentially, it's like putting repelling magnets on the obstacles and an attractive magnet on the goal. The algorithm minimizes the amount of repelling to generate the shortest path using depth data. Then the vibration bracelet guides the user in the direction along the path. Sentry mode ensures the safety of our users. Whenever they feel like they are in danger, the user can either press the button in the haptic bracelet 3 times or say Atheia, Sentry. This sends an emergency message to the user's contacts containing a distress message along with the user's locations. In this demo, we show Sentry mode being activated by pressing the button 3 times, as shown here.
Activating Sentry.
Atheia sends a emergency message, which is shown on the right. The following feature is last seen. Last seen returns when a specific object was last seen by the user. Every detection made with Atheia is backed on Firebase. Each detection is associated with a location and a time. That way, when a user asks when they last saw a specific object, say a keyboard, we carry through the stored detections and return when and where the object was detected, as well as the nearby objects. When Wi-Fi is not available, detections are stored locally in the app's core data. When Wi-Fi is available, the detections are uploaded to Firebase.
Find keyboard.
Keyboard last seen at home at December 16th at 8:32 p.m. next to 1 laptop, 1 display, and 1 lamp.
For facial recognition, we use Amazon Recognition to accurately recognize faces. The user can upload pictures of common faces, so their friends, their family, etc. With more photos, the recognitions can become more accurate.
Atheia, who is this?
Irfan Nafi.
Our text recognition algorithm returns any text in the user's view field as well as the surface it appears on. We use Azure Read API to not only detect text, but to also form bounding boxes indicating where the text is. Object detection generates bounding boxes as well. So if the bounds for the text and object detection exceed 85%, we assume that the text was written on the classified object. So this is best shown in our demo.
Atheia, description.
Description.
Person playing with basketball outside a house.
Atheia, scan. Atheia, text.
Box says Tylenol acetaminophen extra strength.
So that's text recognition. Following feature is VQ&A, which stands for Visual Question Answering, and is done with MMF, a multimodal framework. MMF is like a Frankenstein of leading image text systems and image captioning. It accepts an open-ended question and returns a very specific answer. So in our demo, we ask, where is the blue shirt? And MMF, or View Q&A, returns left, as the blue shirt is on the left. Atheia also supports offers multilingual support to help out anyone across the globe. So we use a combination of Azure translation services and localization services to do so. The user has the option to select their language, then when they give a voice command, their speech is parsed such that we can identify what they are trying to activate. We translate the outputs of the request on the virtual machine through Azure's translational services. The output is returned to them in speech in their native tongue. So this demo is View Q&A being activated in Korean.
Atheia, where is the blue shirt?
Left.
So that's the English.
Atheia, 티셔츠 색깔이 뭐야?
빨간색과 파란색.
Note that it's not just View Q&A. Every feature as well as the app's UI will be translated in the user's native language. So finally, we have our Haptic Bracelet. This isn't really a feature per se, but it's necessary for search and Sentry. In search, the Haptic Bracelet vibrates in the corresponding direction to avoid obstacles and to guide the user towards their desired object. Again, in our demonstration, we use LEDs, but in actuality, the device contains vibration motors, shown in gray. The device also has a button which can activate Sentry mode. If the button is pressed 3 times, this is a quick activation of Sentry, which sends a text message as long as the user's location to the user's emergency contacts. And to accommodate all wrist sizes and to be as adaptive as possible, we designed a watch strap which can be resized, and we also designed the strap in 2 sizes. So our features were a culmination of the people and co-designers with visual impairments that we talked to. Over a course of a year and 5 prototypes, we interviewed several co-designers to gain a deeper understanding of the presenting problems and the features they wanted to include in their desired device. It was a struggle trying to find the right form factor that would address their desire for a sleek, accessible, and affordable device that would suit their lifestyles. As a result, we resorted to advanced technology that iOS systems have, while addressing the battery life concerns with current market devices and accessibility with minimum monthly subscriptions. Moreover, we included offline modes to market the system to users with spotty internet connection. The offline systems was relatively intuitive to implement with a partnership with Ultralytics, which provided us with YOLO v5. However, we needed a way to organize the backend system for a variety of users and the ensemble models and services we utilize.
For scalability and commercial viability of our device, we decided to host our backend on Azure Virtual Machines. With its expandable storage and variety of SSD settings, we were able to use the Azure's VM security to ensure requests from the gloves were met. In addition to the virtual machine, we were able to take advantage of Azure's SDK for Python to make sure this process is simpler. Using Azure's computer vision endpoints and services, we were able to use the advanced models in an ensemble with the YOLO and Mascar CNN models. After the instance received from the image from the teensy, we were able to create an inference on both of the endpoints previously generated in the process and created a JSON consisting of the object's names, respective accuracy, and location in the image. As you can expect, running 5 different algorithms simultaneously and then filtering through every single output will yield pretty accurate results. Our next problem was finding a way to effectively communicate the detected objects to the user. People without visual disabilities can easily see the objects around them, where they're located, and how they're interacting with each other. However, this is very difficult to describe in a concise manner and can get very convoluted very quickly if there are a lot of objects with several different interactions. We realized that the simplest and most concise way to relay this information would be just to say what objects we're detecting along with their frequency. With this solved, we moved on to our next major hurdle, detecting text. There are several technologies that are able to that are already capable of detecting tests in a fast and accurate manner. For our text feature in the device, we used Azure's AI service, Read API. After creating an endpoint client with the service, we were able to use the text extraction from image features to parse and read all the text from the image in the same way it appeared in the image. In addition, users could also read documents and recognize brands with the rest of the Azure's cognitive services. The problem with text detecting solution is that they don't distinguish where the text was detected, but rather just arbitrarily output whatever text was detected, no matter how subtle or out of place. Azure's API was no exception to this, so we started to develop an algorithm that could filter through irrelevant text detections. We continued to develop this algorithm until we discovered a tool developed by the Facebook research called Atheia. Atheia is a deep learning framework that supports vision and language processing with the ability to effectively answer questions about an image detail. By using PyTorch, Atheia gets to be very modular and flexible, taking advantage of multiple tools, references, models, datasets, etc. This allows Atheia to effectively answer questions about an image detail. For example, say that someone gives you money in varying bills. For people with visual disabilities, it's very difficult to distinguish dollar bills without being dependent on someone or something. If you take a picture and ask what's the value of the dollar, it will return a high confidence value of the right amount. If all of its outputs are of low confidence, then we simply return I don't know the answer to that. In addition, we were able to capture the essence of a user's environment by utilizing Azure's description cognitive service. But how exactly do we communicate between the iOS device and effectively run the ensemble? Well, Redis is the answer. To process a singular request from a user, we utilize combinations of a backend server endpoint API, Redis, and dedicated GPU workers. So, when the user asks for a certain result for online modes, it queries the backend server and queues the process in a Redis queue. Dedicated workers working in a parallel have partition memory allocations on multiple GPUs with a mirror strategy framework and comb through the queue while predicting outputs. The backend updates the results in the database and tells the app that the request has been completed. Of course, load balancing, throttling, and DDoS prevention are also run as a safeguard. We aren't too sure of the limits of the process, somewhere around 100 for around 2 GPUs running concurrently. But as we scale for more users and become sustainable, we will have the financial backing to deploy our models as an endpoint on Azure. Doing the process locally just gave us more flexibility for development, and we'll transition to Elixir and use Azure Cloud functionalities to offload this process. So, with multiple requests, it causes workers that might take too long depending on the current concurrent requests received. And to avoid that, we have an automatic timeout that switches to the offline motion option on the phone if the latency time is too long. We're also looking to have distributed feature machines. So for example, MMF has its own dedicated system. And as we acquire funding, that is definitely possible in the future. To communicate between the two systems, Redis is utilized to tell the VM to process a user's endpoint prediction based on user data. Because this is in real time, latency is extremely minimal of around 4 seconds for online because of Ensemble and 2 seconds offline. In the future, because user privacy is something that we thought about a lot with regards to encryption and handling personal data that users don't want people to see. To combat this issue, we have dedicated a private RSA key, seed, and service account deployed with the app so only the user can read data from the encrypted database with their credentials. So, after authenticating the user, SHA 5112, with a constantly updating seed and account information hashed together, the data is retrieved through a public-private asymmetric RSA key system. This ensures that only the user can see their own data, while us and other users can't, while simultaneously preventing attackers from generating exploit vectors. Atheia falls in the market for wearable devices in the health industry, a market that is growing rapidly. According to a study conducted by Accenture, the market for wearable devices in the health industry has gone from 9% in 2014 to 33% in 2018. Our competitors are other wearable devices aiding the visually impaired. As of now, we plan to sell our product commercially at a price of $40 for the Haptic Bracelet and a $10.50 monthly subscription for the mobile app. Our target audience is people who are visually impaired, ranging from total blindness to mild visual disabilities. In the US, over 3.4 million people are classified as legally blind, and 285 million people suffer from visual impairments worldwide. Based on the increasing age of the population, it is projected that in the next 3 decades, that figure will increase to 570 million. Based on our research, which has taken into account the employment status, income levels, and geographical locations of visually impaired people, we concluded that only 5.02% of them would not have the resources to buy our product. That leaves nearly 3 million beneficiaries in America and 240 million beneficiaries in the world. However, we will not be reaching those people alone. We already have a partnership with the National Industries of the Blind, NIB, as well as the visually impaired members of the MIT's Humanistic Co-Design Initiative. Through the NIB, we came into contact with 30 initial user testers. Additionally, we have amassed funding from our grants that consist of $5,000 from the Maximus Foundation and $6,000 from AWS. Our current next steps are to roll out user testing once COVID restrictions loosen up. Again, we are students and always willing to learn, so if you have any expertise you could offer us, any additional opportunities for mentorship or user testing, please let us know at this email, projectatheia@gmail.com. If you'd like to follow along with our journey or to find more about our project, there is our website and below is the video that sums up our device. We hope through our device we could inspire the youth and be of aid to one of our most resilient communities, the visually impaired. Thank you.